All right back at it. Let's talk about detectors for GC. We talked about column technology, we talked about temperature programming, but how in the world are we going to detect the chemicals when they elute from our GC column? We need a transducer, don't we? We need a way to detect the presence of materials when they elute. And these are detectors. So for GC, there are many different types. This is a partial list of some of the more popular. Thermal conductivity, flame ionization, electron capture, photoionization, flame photometric, Hall conductivity, and then we have the GCMS. You know what, that all of these typically have these abbreviations, these letters, which are very commonly used to denote which detector people are using. So we'll want to pay attention to those abbreviations as well, because sometimes the person may not say a thermal conductivity detector, they'll just say TCD and basically assume that you know what they're talking about. So let's kind of go through them and understand these. The first one I want to tell you about is the thermal conductivity detector, which is the TCD. One of the most common detectors used in GC, and the reason why, pretty inexpensive, easy to understand, but moreover, it is a universal detector. It can potentially respond to all substances, okay? Now, this TCD works in the following way. You build a little block. It's usually metallic, okay? And inside there is a filament that's right there, okay? That filament basically is pretty interesting in sort of the center piece of this detector. Because what we're going to do is we're going to pass a current through that filament. It's going to be a tungsten wire, just like a light bulb wire, okay? We'll pass a little bit less current through it so it doesn't heat up as much. But when we pass the current through, it will heat up some, okay? And depending on the current I pass through it, it will heat up to a certain temperature. Now, think about for a second what the factors responsible for that temperature are. Well, one would be the current, right? More current, more heat generation, right? But let's just say I keep the current constant. What other factors might affect the final temperature of that tungsten filament? Well, one thing that comes to mind to me is the rate of loss of heat energy from the filament. Now what I'm going to do is I'm going to take the gas flow, this is my carrier gas and or my sample, and I'm going to continue to perfuse it through this chamber to the outlet at a constant rate. And when I do that, that gas flow really has the capability of removing some heat from the filament. But if I keep my flow rate constant, and if I keep my gas composition constant, the rate of heat loss from the filament should really be constant over time. But nonetheless, the gas flow will remove some of the heat from that filament. Now, okay, that makes sense. And maybe I reach an equilibrium temperature, but how does this serve as a detector, right? Think about it. If I inject a sample onto my column, sooner or later, the sample molecules will elute from the column and also pass through this cell. And when those sample molecules make it through the cell, the gas composition changes ever so slightly. It's no longer just the pure carrier gas. Now it's the carrier gas plus these other molecules, right? So if that's the case, it turns out that the sample molecules will remove slightly different amounts of heat energy from that filament. Believe it or not, that small difference in removal of heat can change the temperature of my filament. Now, if the temperature of my filament changes, a very interesting thing occurs. The filament's electrical resistance depends upon its temperature. Its electrical resistance depends upon its temperature. So if the temperature changes, its resistance will change. And we can actually sense this ever so slight change in resistance using a circuit called a Wheatstone bridge. We don't have to know the details about that, but it's just a fancy way to detect this change in resistance. So this is the thermal conductivity detector. We sit back, we measure the change in that filament's resistance due to a change in temperature, which is caused by differences in thermal conductivity or heat removal ability of our sample molecules compared to our carrier gas. Now, this works really great. It's a universal detector, can detect just about everything because just about everything has a different thermal conductivity than your carrier gas, right? But the problem with it, down here at the bottom, it has very limited sensitivity. You generally need pretty high amounts of sample to be able to detect it with a TCD, okay? You can't do ultra trace analysis. It's just not gonna work. It's not sensitive enough. But since it is a very universal detector, it responds to everything. It's used a lot. You'll find this a lot in the labs. The reason being is, well, it's very, very general purpose. I can detect lots of things with this stuff. So why not have it around, right? Now the next detector, FID, is also very, very, very popular. It really rivals the TCD in terms of popularity. It's called the flame ionization detector. Again, as the name suggests, there's going to be a flame and we're going to detect essentially ions. No big surprise, right? So what type of analyte can you detect with this? Well, usually this is the realm of detection of hydrocarbons and other gases which are combustible. So if any of you ever go, working in the oil industry, petroleum industry, you might use a FID to analyze samples of whatever it is you're analyzing because it's really the realm of hydrocarbons. This is an extremely sensitive detector for hydrocarbons, as it turns out. So how does this one work? Well, what we do is we plumb our column and the gas flow down here at the bottom, at this port, okay? And the rest of this is just a detector. So things elute basically in that direction. They pass through this central bore, or they exit the column and are mixed with another gas right here. And note that gas is hydrogen, H2, which we have to buy a tank of, okay? There's a pressure regulator to get the right pressure and flow. We mix it with the sample up into this region where it mixes with air. Okay, this is from a second tank or some sort of air supply source. That mixture of materials is passed up here to this region right here, which is our flame. So there's a little burner basically inside there. Tiny little burner, much smaller than a Bunsen burner. But we ignite a hydrogen flame. You usually have to do that at the start of the experiment by providing a spark or some sort of flame. All right, so you ignite the hydrogen flame right there at the tip. And basically your entire sample flows into that flame. Now we know hydrogen is flammable, it reacts with oxygen to make water, we could support a flame. And whenever the material from our column and our sample enters that flame, it basically combusts or burns up. So it's a destructive detector, okay? But how does this detect anything? I mean, I get the hydrocarbons flow in, they're flammable, they burn, they combust, yeah, great. Okay, how does it detect anything, right? We haven't talked about that yet. The way it happens, this detection event happens, is the metal body of our burner serves as an electrode. We're going to hold it at a negative polarity. We're going to have a second electrode as well. It's called the collector. Up here at the top, it's going to be our positive polarity electrode. That's this one. And it's usually like a little cylinder that's kind of placed above the flame. All right, so that's our positive electrode nonetheless, a collector. Okay, so a couple electrodes, maybe we can bias these, we can apply a voltage, like a plus voltage and a minus voltage, right? But how does it serve a detector? We haven't explained that yet. Okay, well, the key are chemical reactions. Now the thing is that the chemistry of flames are extremely complex, right? Active research programs center upon studying the chemistry of flames. Very, very complicated. So we're going to have to simplify. Our simplification here is that if a hydrocarbon enters the flame, it undergoes a series of complex reactions in which it combines with oxygen to form ions that have the generic formula CHO. Now, this is much more complicated. There can be many different carbons in a particular ion which is produced, but this is just kind of a generic overview of a chemical reaction that could occur. We produce these ions, but we also produce electrons in the flame as a result of these individual combustion type reactions that are carried out. Now, if we're producing ions and electrons in the flame in this region, and I bias these two electrodes, in my flame ionization detector, where will the electrons go and where will the ions go? Well, the ions would be attracted to the negative electrode, but the electrons are going to fly to the collector or the positive electrode, aren't they? So the collector, as the name suggests, collects electrons because it's positively biased over the positive voltage. The electrons collide with the positive electrode, the collector, and those electrons can basically flow through an external circuit out here, or we could place an ammeter to measure the electron flow or the current produced by these electrons. If we can measure the flow of electrons through that circuit, we can link that back to the quantity of the hydrocarbon present. We have built ourselves a detector. And not only have we built ourselves a detector, but since chemists or in physical science in general, right? I don't want to give credit to only chemists, but measurement scientists are really, really good at measuring current to very, very low levels. Because of that, this is an extremely sensitive detector. We can detect down to the femtogram levels of hydrocarbons. That's 10 to the minus 15 grams. Very, very low levels of hydrocarbons can be detected. It's a very, very sensitive detector and really quite common. You only have to use some hydrogen and some air, which can be obtained at reasonable costs, generally speaking. And you can measure hydrocarbons at very, very, very low levels. This is the flame ionization detector, FID, very common. Now, another type of detector is the ECD, which stands for the electron capture detector. This one is useful for molecules containing atoms which are very, very electronegative, oftentimes halogens. So this detector is useful oftentimes for like pesticides analysis because pesticides frequently contain halogen atoms. But you got to have electronegative atoms in your molecule that you want to analyze if you're going to use this. But if you do, the electron capture detector is also extremely sensitive for molecules containing highly sensitive or highly electronegative atoms, okay? So how does the ECD work? Well, basically what we're going to do is we're going to have a beta particle source. It's a radioactive source producing beta particles. Now, beta particles are just like electrons, except they emanate from the nucleus of atoms during radioactive decay events. Nickel-63 is a very common beta particle source. Okay, so that's shown here in these blue bars on the side of our electron capture detector. Now notice what we do is we are going to flow into the bottom, continuous flow setup, our eluent, which basically means the material that flows off of our column. So that's going to be our carrier gas plus our sample. So sample plus carrier gas flows in through the bottom into this chamber. Now this nickel-63 source will always be undergoing radioactive decay continually, right? It's always undergoing this process. And since it's a beta particle source, these beta particles, which are again, essentially for our purposes here, equivalent to electrons, will be constantly be released from the nickel-63 source, okay? Now, in addition to the carrier gas, we're going to put in there essentially a plasma support gas, which is going to basically be some argon or maybe a little bit of methane. The details of which are not going to be too important for us. But when that's present in that region near the nickel-63 source, the electrons that are emanating from the nuclear decay events will collide with that gas, thereby causing an ionization to occur. The electron is a relatively energetic particle, collides with the gas, say argon for our purposes here, causing argon to ionize, producing more electrons. So in this region in through here then, due to this flux of electrons from the radioactive decay, we actually produce a gas phase collection of argon ions and electrons. This is like a plasma state, okay? So in through here, we've got this constant flow or flux of electrons being produced. Now, what are we going to do with this? Well, we're going to make a positively charged electrode in the center called our anode. And as we know, electrons are negative. This anode is very likely to collect these electrons. And indeed, that is exactly what happens. The anode continually collects the electrons which are being produced due to this radioactive decay and this avalanche of ionization which occurs within our chamber. That doesn't sound very efficient or exciting as a detector. We haven't talked at all about how in the world we're going to use this to detect anything. I mean, it just seems like there's going to be this constant flow of electrons to our anode, and that's it. And indeed, that is what happens. There is a constant flow of electrons to the anode. But if our sample is introduced into that chamber, the sample molecules will also get up into this region where this collection of electrons and gas phase ions exist. And the sample itself may undergo degradative processes. It may degrade. But let's just say, for example, I had a molecule CH3F, and I'm just making this up as we go, okay? CH3F, we put that up here in this region. And let's just say it fully degrades into carbon atoms, some hydrogen atoms, and some fluorine. No, fluorine is highly electronegative, right? And that's why I use this example, of course. If you put fluorine atoms into that mix, since fluorine is so electronegative, might it have a tendency to capture an electron? I'll say to make F minus here, okay? But really the capture event is what's important. So if that's the case, then the presence of fluorine in that region here, where we have this cloud of electrons, will really change things a little bit, because the fluorine atoms which are present, or really any highly electronegative atom which is present, maybe it's chlorine, maybe it's nitrogen, any highly electronegative atom, right, we can put in there, they will capture some of these electrons which are being produced by this nuclear decay event and the subsequent avalanche of ion and electron formation that results. They will capture some of those electrons. Now, what's going to happen is that's going to reduce the net flux of electrons to the anode. So if I monitor the current in time at that detector, okay, let's just say at first it's only the carrier gas and support gas, okay? The current will be up here. It'll be pretty high because those electrons will be forming, they'll be flying to the anode. But then I introduce my sample to the mix, and my sample has this highly electronegative atom in it. Well, those atoms are going to capture some of those electrons. So what happens is the current actually drops off until my sample is removed from the mix, and then the current normalizes back out again. So I actually see a drop in current that's caused by the capture of electrons by my highly electronegative particles. And that's essentially how this detector works. It's quite sensitive for highly electronegative elements, and only highly electronegative elements. The other elements that aren't so electronegative really don't produce a big signal. So the ECD is commonly used for things which are really, really, really electronegative, okay? If you don't have that as your analyte, probably not a good choice to choose this. So we want to match our detector to the analyte, okay? This is the ECD. Used consistently in environmental type analysis. I mentioned pesticides. The next type I want to give about is the PID. This is the photoionization detector. Another interesting detector. It's fairly general purpose. It uses UV light from a gas discharge lamp essentially to ionize sample molecules. Let's take a look at how this works. Up top, we've got a UV lamp here, an ultraviolet lamp. Now, this is not necessarily one of our decuring lamps that we talked about earlier. Instead, it's actually a special lamp that produces wavelengths at even lower wavelengths, well below 200 nanometers. That would be typical for our UV spectrometer. This produces light usually either at 106 or 149. There's a couple different designs for that lamp and a little bit different compositions. And based on which one you choose, you can either get light at 149 nanometers or 106 nanometers wavelength. This is way below 200 nanometers. This is way down in what's typically called the vacuum ultraviolet. The net result is that the energy of these photons are very high, oftentimes in excess of 10 electron volts. That doesn't mean a whole lot to you. But what I'm here to tell you is that these photons are ionizing radiation. They can ionize molecules. Now, usually that wouldn't be so healthy, like for our skin, say, for instance. We wouldn't want to be exposed to this type of radiation. But in the PID detector, it's kind of a good thing. The reason why is because if we have our effluent or eluent from our column, and we flow that gas containing our sample molecules into this region right here, it can be illuminated by our UV light. Now, it passes through a magnesium fluoride window. That's because that's UV transparent. Okay, that's just a window to seal off the light source from the sensor or the detector flow cell. Okay, but light passes in through here where it interacts with our molecules in this region. Now, the molecules are going to absorb this light because we can even start to promote sigma to sigma star type transitions. We can break bonds. We can ionize things, strict molecules of electrons. So it's going to be highly absorptive in that region. Our molecules will highly absorb this light right there in that reaction region. And what's generally going to happen is our molecule will absorb the photon's energy and become ionized or stripped of an electron. This process will occur right in there. If that happens, we produce electrons, and boy, you guessed it, we just have to bias these electrons at a positive and negative voltage, don't we? These electrodes which are present. We're going to bias these metallic electrodes at a positive and negative voltage. We're going to apply a voltage. Electrons which will be produced will certainly fly to the positive electrode, be collected in an external circuit, producing a current. That current will be proportional to the analyte quantity present in this illumination region and the rate of this photochemical reaction, basically, which is dependent upon the amount of M we have. We've built ourselves a detector based on photoionization. This is the PID, photoionization detector. Now, the last detection device I'd like to tell you about will take me a few minutes to explain here, but this one's really cool. This one's GCMS, which stands for gas chromatography, and the MS, it stands for mass. And this is really a high-end detector for GC. And the reason why is because GC allows you to separate your molecules, but mass spectrometry starts to give you a lot of information about what your molecules that you separated actually were. It allows us to provide confirmation of molecular structure. It's a very information-rich technique as a result. Now, it may set you back, I don't know, maybe a better part of $100,000 to buy one of these. But the data that you get from it is really unparalleled in terms of ability to do qualitative analysis, to understand what the materials were. And oftentimes, if people get arrested for having drugs or blood doping in the Olympics or something like that, right, using banned substances, they will need to confirm the presence of that illicit substance. They're using GCMS methods, and the reason why is because it is kind of the gold standard. I mean, if you get a signal by GCMS that corresponds to that illicit substance, boy, it really probably is. There's not a whole lot of tricking these devices, okay? So let's talk about GCMS, how it works, and really what it does, because it's a little bit complicated, but it's not anything that we cannot understand. So first off, the GC portion of our device is really down here in the left corner, and all we're really getting GC-wise is the outlet from our column. This would usually be a capillary column. By the way, we usually use capillary columns with this technique. And the outlet from our capillary column would be consistently passed to this little box that's over here in the middle. And we call that entire box, as it turns out, the source, or the ion source. Ion source is more descriptive because this box is going to basically make ions for us out of our analyte molecules. How in the world does this happen, right? Well, it happens through a process called electron impact ionization. EI, electron impact. It's the most common source. There are other sources available, but the most common is EI, electron impact. The way that this works is we basically create an electron gun up here at the top through use of this hot filament. What this is really a wire. Okay, it's kind of coiled. It's like a tungsten wire. We're going to pass an electric current through it by application of a voltage. Now, the passage of electron current through that little wire basically creates an abundance of electrons, we'll say, within the filament. And it turns out that some of those electrons are emanated from the filament, filament basically gives off these electrons or produces these electrons, we'll say, okay? Now what happens after that, these electrons are produced. They are accelerated towards this positive electrode called this collector trap electrode at the bottom. Notice here that we apply 100 volts DC potential. That's 100 volts positive right there, right? So once those electrons are produced, they are going to say, hey, there's a positive electrode down there. I am headed that direction. And they will eventually collide with the collector electrode, okay? Now that doesn't sound very interesting by itself, just accelerating these electrodes from the electron gun, the filament, into this collector electrode. But it is kind of interesting actually, because we assure that the electrons go from top to bottom. In addition, during their journey, they're really accelerated along the way under this 100-volt potential difference. They're really, really, really accelerated under this 100-volt potential difference into very, very high velocities, relatively high kinetic energies on an atomic scale or molecular scale. So what do we do with this electron flow from top to bottom? Well, we put the outlet of our capillary tube somewhere in the region where if molecules get eluted from the tube, they basically interact with this flow of electrons. And ultimately what happens is this up here. One of our analyte molecules, abbreviated by M, may collide or impact with one of these high-speed electrons that are flowing through this source. If that happens, a cool thing occurs. We ionize our molecule M. And in that process, we strip it of an electron. So we're always making M+1 ions. That's the molecule minus an electron. And it says here 2 electrons are produced. Well, one came from the molecule. The other one is just this one we started with, okay? So we produce a net 1 electron, if that makes sense. And we make the M+1 ions, more importantly, right in this region and through here. So this source, all it does, this electron gun basically collides with our molecules to produce ions of a molecule. Now that's required for mass spectrometry because you do mass spectrometry on ions. You have to ionize things before you can measure them by mass spectrometry. And you know that's why, generally speaking, there are a large number of different sources. They all work in a different way, but you have to have an ion source. Electron impact is the most common for GCMS. There are a few others, but this is the most common. Now, what do we do with these ions after we make them in that region? Remember, we're making M+1 ions there, okay? Now we can do the mass spectrometry. Ultimately, what happens is we accelerate those ions from left to right. We accelerate them towards this little hole down here, okay? And if they make it through that hole, we can detect them and measure them. But most of the ions won't make it. We'll more on that here in a second. But at first, we accelerate them from left to right by application of a voltage using what's called ion lenses or accelerators, okay? It's just basically charged plates that pull the ions once they're produced towards the right, towards that little hole, okay? Now that's not the only force that these ions are gonna encounter. As it turns out, they will encounter other forces. So we accelerate them, we give them a certain kinetic energy. We start them on their way towards the ending of that hole. But boy, we're gonna make this journey a little bit more difficult. Because what we're gonna do is we're gonna make the ions fly through the quadrupole region, meaning 4 poles or 4 electrodes. Here's 1, 2, 3, 4. These are basically stainless steel rods that are precision engineered and placed at a certain distance to one another. Now, these rods, the negative ones are basically electrically connected, and the positive ones across from one another are also electrically connected. And we aren't going to just put these rods there. They're going to serve some other purpose. We are going to wire the rods up to a power supply. Here's where things get a little crazy, okay? The power supply that we wire these rods to can apply both a radio frequency AC waveform or alternating. It's like basically a sinusoidal wave that oscillates at radio frequencies, that particular frequency. But the rods are also wired into a DC source. Okay, so both AC and DC waveforms are applied to these rods. Now DC is, if you look at constant or voltage over time, is constant, okay? But AC is like a sine wave. Okay, so what we're going to basically do is apply both of those to these rods in a really precise way. We're going to basically scan or increase the voltage, the DC voltage over time, while keeping this radio frequency also superimposed upon that waveform. Now what happens? Well, remember, I'm making my M+1 ion and I'm shooting it or accelerating it down this way, all right? Now, if my ion, we'll say is too heavy, it's kind of a big heavy ion, what happens is that the ion will experience the DC wave form more so than the AC. It might kind of oscillate through the AC waveform a little bit, but it's got so much momentum that it can't really experience that full AC waveform. And eventually what happens is, since it's too heavy, its trajectory will take it to collide with one of these rods inside the device. Now, on the other hand, if my ion, which I introduced here, is too light, what happens then is it's just a charged light particle. Well, light particles, they're not going to have very much momentum. I mean, they're accelerated this way, but gosh, it sees that AC field, and what happens? It just oscillates like crazy. And if it's too light, it will oscillate in the AC field and end up colliding with one of these rods. And if it collides with the rods, it's eliminated, it's removed, okay? But for an M+1 ion, we'll say that's just right. It's like the porridge and the three bears or the Goldilocks, right? If it's just the right mass, what can happen is you inject it into this region and it starts to oscillate or dance at just the right frequency. So just as it starts moving towards this electrode, that negative one up top will say, well, the RF voltage flip sign, oh, it goes away from that electrode now. And it oscillates just right. It can move towards it, away. It kind of follows that cycle of that radio frequency, right? All the way through. And boy, if it's just right, it'll make it through that hole. But ions which were too heavy were removed under the primarily DC influence. Ions which were too light were removed primarily under the AC influence. But just the right mass makes it through. So basically this quadrupole thing, you can filter. It only allows ions of a certain mass through, and only a very precise mass through. And that's it. Everything else is removed. When you say, okay, I guess I understand that, Professor Thompson, but I mean, can this device only measure one ion then, one mass? And the answer is no. It can measure lots of different masses, usually up to a few hundred AMU. And the reason why is because if we want a different mass to make it through that hole, all I need to do is adjust the DC and AC waveform combination. And if I fine tune that a little bit, I can make a different mass to make it through the hole, heavier or lighter, depending on how I adjust the DC. So what these quadrupole mass analyzers basically do is they scan or change the DC and AC waveform to get the complete mass spectrum. And what I mean by that is they scan from low masses allowed through the hole up to higher masses allowed through the hole. And as a result, we can measure all the masses in a complete scan. And the cool thing about these quadrupole mass analyzers is they're able to do this complete scan really, really rapidly, even less than a second. Okay? You can complete mass spectrum in less than a second. So think about the ramifications of this. Okay, we normally talk about a chromatogram, which is detector signal as time, and we see a series of peaks. So basically what I'm saying is, at each point in time, when a molecule elutes from the column, that molecule gets in our source, it's ionized, we can record a complete mass spectrum, like every second or less than a second. And the data that the mass spectrum gives us then is a signal versus mass to charge. So at every single point along our chromatogram curve, we can record one of these figures. And what these look like actually is something like this, okay? It's a series of peaks. And each of these peaks correspond to a particular m over z, which stands for mass to charge. Now, fortunately for us, in this form of ionization, all of our ions are +1. In electron impact, we say they're +1. So the z is basically a 1, okay? So this axis basically becomes like a mass axis in AMU. And we know that if we add up the parts from the periodic table, we can predict what the mass of certain ions are, right? So because we know the mass, gosh, we kind of know what the ions are, don't we? And that's kind of a very, very, very powerful thing, I think, okay? Because not only do we get the retention time behavior in the chromatogram, what time it elutes, but we can also figure out what the masses are. So that tells us about what that substance might be, even if we don't know, okay? Now, before I go on to data interpretation, I want to talk a little bit about this part of the figure up here. All this is the detector for the mass spectrometer. It's called an electron multiplier. It actually works a lot like a photomultiplier too. The ion comes in, strikes a cathode, which drives ionization events, production of electrons. They're then multiplied through several diodes, just like the PMT, and finally collected, producing a current. It's a sensitive way to detect ions. It's commonly incorporated into these GCMSs. Now, let's talk about data analysis from electron impact ionization. A sample mass spectrum looks something like this. So if you inject this molecule into the mass spectrometer using EI, ionization, and then quadrupole mass analysis, you end up seeing something that looks like this. Okay, now what in the world is this figure? Well, it's a plot of abundance, which is really a proxy of detector signal versus my good friend mass to charge. And remember, we're dealing with the +1 ions here. This is really kind of like a mass axis down here. So each of these numbers are basically the masses of a particular signal that was observed in our quadrupole mass spectrometer. This again being our detector signal, so bigger peaks, bigger signal, right? Now notice here that this is a relative abundance. Let's talk about that first. What the analyst did to make this figure was he or she found the absolute biggest, largest peak in their spectrum, which for this figure occurs at m over z 141. Okay, this so happens to be the largest peak. And they assign that peak a value, or that signal, a value of 100 to convert this to a relative scale. And all other peaks are normalized to that. Now, in a mass spectrum, that biggest peak is called the base peak, just the terminology. We call that the base peak. It's the largest peak in the mass spectrum. So 141 is said to be the base peak here. Now, for this particular molecule, pentobarbital, if you add up the masses of the parts, you end up getting 226 AMU as your molecular weight, okay? So you'd expect to see a huge, based on what I've told you already, you'd expect to see a huge peak for pentobarbital at 226. But if we look at the mass spectrum, there's only a tiny little peak there. Most of the peaks are much smaller than that. Now, the peak which occurs at the expected mass to charge for the molecule as a whole is called the molecular ion. The molecular ion, that's where it would occur for the molecule as a whole. But we don't see a huge molecular ion peak at all here, do we? We see peaks everywhere else, but not much at 226. So let's explain that. Why is that? That's a bit curious based on what I've told you so far. It turns out that I didn't give you the complete story. And I need to now. This electron impact process that's occurring in our source, where we accelerate the electrons to ionize our molecules, this process is not so gentle. I mean, it probably didn't sound gentle at first, right? We're accelerating these electrons, we're shooting them and colliding them with our molecules. Well, it's pretty energetic. It's not so gentle. It just so happens that for most molecules, a lot of molecules, when we bombard them with these electrons at high energy, the molecules will become ionized and stripped of electrons, but they also fragment or break apart. They fragment in the source. They break up into individual fragments or parts. And that's actually what we're seeing here. So our pentobarbital, when it was ionized, it fragmented into smaller bits and pieces of the molecule. And that's what's producing, all these other peaks that we're seeing, okay? Now, here's the thing. Now, that sounds like a bit of a bummer at first, right? So, well, my molecule fragmented. That kind of stinks. I mean, I was hoping to see a nice molecular ion peak at 226, and I can quantify things based on that peak. I have confidence that it's pentobarbital. This fragmentation thing is just making a big mess out of my spectrum. But there's kind of a good part to this. And the good part is that fragmentation patterns for a particular molecule with a particular kinetic energy of the electrons that are produced in the source, fragmentation patterns under such conditions are kind of like, again, a fingerprint. What I mean by that is this molecule, pentobarbital, when it fragments in an EI source under this set of conditions of electron energy, will tend to always fragment in this observed pattern. You'll get these peaks observed. It's kind of like a fingerprint for that substance. So, well, let's just say that I'm really into this GCMS thing, and I do analysis of thousands of different compounds. I test out many, many, many different compounds on my mass spectrometer after GC. And I record the resultant electron impact ionization spectra. Couldn't I build maybe a library of all my spectra that I saw? And then perhaps I could run an unknown sample and on my computer record a mass spectrum. And if I wanted to, maybe if I got really good at this and was proficient at computer software development, I could even develop a software package, a library software package, where I could compare the mass spectrum that I obtained in an experiment with my library. I could basically search my library to see if I've seen a spectrum like this before in all the things that I've tested, right? Do I see something similar? And in fact, manufacturers of GCs these days will sell you software that have this exact library search feature that I'm describing. You can actually search their existing library of literally thousands of compounds to see if the fragmentation pattern that you observe is similar to what's been observed previously for a known standard. And gosh, if it is, then you've gained some confidence that what you are observing is the actual substance you think it is, whether it's a cocaine metabolite or some drug that an athlete might take to boost their performance. You gain confidence that, hey, what you're seeing is really that substance. The mass spectrum will help you tell you that. The fragmentation pattern will help tell you that. And the third thing that will actually help tell you that is the GC retention behavior. Remember, all this occurs after GC. You still have your chromatogram, your list of peaks in time, right? Now, if you think that this peak right here is an illicit substance, well, maybe you can buy that substance from a chemical supply house if you've got the legal authority to do so, which sometimes you can get approval for. If you inject it on your GC for a standard, a pure substance, and you get a peak right there, okay, well, it's the same retention time. Now, if you take the data from the mass spectrum for both of these, okay, and for the known sample, if you see a mass spectrum that looks like this, and then you run the same experiment for the unknown sample that you got, from the athlete that you suspect of doping, and you get something that looks like that, it's the same, right? So you got the same retention time, same fragmentation pattern. Well, that guy might be in, or gal might be in a little bit of trouble. It seems like maybe they're guilty of doping in such a case, because you got so much evidence, so much chemical evidence, the same fragmentation pattern, same retention time. That's pretty strong, convincing evidence to an analyst that, that substance was really present in that athlete's blood. Okay, so GCMS is used a lot in analytical labs throughout the world. Very popular method. Again, the instrumentation is not particularly cheap. However, the data that you get is just remarkably informative, and that's why people use it. All right, so I'm going to end this video now, and we'll go on later.